Greetings, Earthlings! Today we're going to take a look at the instruction set of the new, improved, yet still utterly stupid computer. Let's start by looking back at the original instruction set, and as you recall, we were limited there by the amount of microcode memory available. So it's not a very robust instruction set, shall we say. It's rather wasteful, and there's a lot of unused potential opcodes in there. Or wasted opcodes. If, for instance, we look at halt, which was opcode 0, there's 8 wasted bits there that could be used to address a memory location, for instance. Well, speaking of accessing memory locations, the first thing we have to figure out is how we're going to do that with this new machine, which has 4K of memory. The original had just 256 words of memory, so we could directly address any memory location with just 8 bits. Since we're keeping the format of 4 bits of opcode and 8 bits of potential address, we're not able to access all 4K of the memory in the new machine. So there are a couple of things we could do here. First, we could make all addresses relative. That would give us a 256-word window in which to address memory, but that makes it hard to access outside of that window. We could use a paged approach, where we have a page register, which specifies a 256-word block of memory. Then we need a way to set the page register, and any access to memory would be relative to that page register. Basically, that's a 4-bit register, and that will specify the high 4 bits of the address, and the lower 8 bits will be in the instruction itself. And another way would be to have indirect addressing multi-word instructions where we have a full 12 bits to specify a memory address. Okay, so for basic branching, we're going to use the relative approach. Now, one thing we could do at this point is we have 8 bits of address. We could treat that as a signed number and go plus 127 minus 128 from the current location. That complicates the hardware a little bit, so what I chose to do there is have 2 different branch instructions, a branch forward and a branch backward. And each one of those has 8 bits of offset. So you can branch forward 0 to 255 instructions. You can branch backwards 0 to 255 instructions. That uses up 2 opcodes. Oh, that's okay. As we'll see, we've got enough opcodes. For the other instructions, loading and storing the accumulator, and the arithmetic instructions, which operate on the accumulator and a memory location, we're going to use the paged approach. So, as I said, there will be a 4-bit page register, and then the 8 bits of offset within that page are specified in the instruction. Okay, so the basic instruction set is very similar. The high 4 bits are the opcode, and for 0 through E opcode, the lower 8 bits are an address or an offset. So we have branch forward, branch back, load accumulator, store accumulator, just as before, add to accumulator. Now, since we've implemented a carry bit in this implementation to support multi-precision arithmetic, potentially, we've also got an add with carry and a subtract with borrow instruction. Then and or, we've added XOR. Not used that much, but, when you want it, you want it, Increment and skip of 0, decrement and skip of 0 stay the same. And, I say they stay the same, but the opcode is different. Oh, by the way, let's back up. Backward compatibility. Not an issue here. There is no existing code that runs on the original stupid computer that we have to continue to support. So there's no reason to keep the opcodes the same as they were before. Had this been an actual computer out there in the wild, and we were trying to extend the instruction set, then we'd have to think about doing it in a way that would preserve the original functionality so that all existing code would continue to run, and only extend it with opcodes that weren't used before. Not an issue here, as I said. Okay, we get down to opcodes D and E, and I was kind of running out of ideas here, so I said, skip if memory location is 0, that may be a useful thing, and swap accumulator with a memory location. So what's missing? What got thrown away? Well, Halt actually got moved into an F opcode. The F opcode was highly underutilized in the initial implementation. So as you'll see very shortly, it's greatly expanded here. So halt got moved. Hang, throw that out. We don't need that. Branch if 0, branch if negative, branch if positive. Okay, we've only got branch forward and branch back here. What we're going to do is add skip instructions, which will use the F opcode. So skip if positive, skip if 0, skip if negative, or something along those lines. So that functionality will now take 2 instructions. You'll have to skip on a condition and branch instead of branching directly on the, inverse of that condition. Deal with it. You've got a lot more memory to play with. Now the F opcode. The F opcode gets very interesting because it was, as I said, it was highly underutilized previously. Just used to read the front panel switches and to access the terminal. Now we've got a whole lot more functionality in there, and a lot of it revolves around these indirect registers, which I've added. So there's 4 registers, IR0 through IR3, which I call indirect registers. I put them in there to make for more efficient memory-to-memory moves, for instance, doing a string copy or something like that, or just a memory move, which you do a lot, and I wanted that to be fairly efficient. So you can see the F0, I'll call it F0 sub opcode, 0 opcode of the F opcode. I don't know how you want to say this. F0, F10, F20, F30, F40, F50, F60, F70, F80, F90, FA, FB, FC. Those all are used to access these indirect registers in various ways. And we'll maybe get into that a little more. Probably have to, so you'll understand it. FD is used to set the page register. The lowest 4 bits specify the particular page, or again, that ends up being the high 4 bits of the address. So FD0 says set page register to 0, FD3 sets page register to 3, and so on. FE and FF contain a lot of other interesting functionality. The original read switches get character from the teletype print character. We also have the ability now with FE4 and FE5 to not have to block when we're reading a character or writing a character. The microcode will, and did in the original, block. For instance, if you're printing a character and there's a character currently being printed, it will block and wait for that to become available. That can waste time, which you might be able to use for something else. So, for instance, in the print case, FE5 lets you test if that print would block, and you can go off and do something else if it is, and come back later and test it again. Similarly, on the input, you don't have to block waiting for the input. You can test it with FE4 and go off and do something else, and then come back until there's a character available. Again, no interrupts in this implementation, so we can't have an interrupt handler, so polling is the best we can do. Okay, then some additional operations on the accumulator and the carry bit. Arithmetic shift right, rotate right through carry. Arithmetic shift left, rotate left through carry. Skip if carry set, skip if carry not set. Clear the accumulator, set the accumulator, that'll set it to all ones. Complement it, negate it, increment it, decrement it. Directly, single instruction. You don't have to have, if you want to increment the accumulator, you don't have to have a 1 stored somewhere in memory and say add 1 to it. Something horrible like that. Use the add instruction for that. No, increment accumulator. I also threw in increment and skip of 0 the accumulator. You may find that useful. Who knows? And decrement and skip of 0, of course. Set carry, clear carry. Okay. And then FFB, FFC, FFD, FFE. These are, as I mentioned before, the replacements for those branch if positive, 0, negative. Skip if 0, skip if non-0, skip if positive, skip if negative. And FFF is halt, and so, of course, that freed up the 0 opcode. Now, this shows the map of the opcodes that are currently defined. This is preliminary still, but you can see there's still room to add more functionality in here, should one so choose. Now, going back to the indirect registers, you could use these as temporary registers. Let's look at F1. F11, move accumulator to IR1. F12, move accumulator to IR2, and so on. So you can store things in there. You can't You cannot move things directly from memory into an indirect register or from an indirect register into memory. They all go through the accumulator. But that should be okay. Okay, you can increment them, you can decrement them, and then you can move through them. So if we look at, for instance, F01, move accumulator to, now the parentheses mean the address specified by IR0, okay? So if IR0 has 27 in it, what that instruction is going to do is going to take the contents of the accumulator and store it in location 27. Let's go down to the F20 instructions. Now we've got an auto increment on that, a post increment. Move the accumulator to the address specified by IR0 and then increment IR0. This is handy if, say, you want to zero out a buffer. Set IR0 to the start of the buffer, clear the accumulator, issue an F20 instruction for as many bytes as you need to fill that buffer. So you probably have a counter somewhere in memory and you're doing like a decrement and skip of 0 on that to tell you when you're done. F30, you can see we can do auto decrement. It's a post decrement. And we can move the other way with the F40 and F50. And then there's the pre-increment and pre-decrement instructions, F60, F70, F80, F90. Move things between indirect registers with FA. Now FB tests. So if you were using this to, say, do a string copy, you can test that for 0, terminating null, and skip if 0, skip if non-0. Okay, that's FB. FC is used, we use the indirect registers also in subroutine calls. So it will jump to the address specified by the register and save the return address in one of the indirect registers, which could be the same one or it could be another one. Now I should mention, I kind of mentioned it, but it was sort of hidden, and I'll make it explicit here. Designing the instruction set is not just sitting down and saying, boom, this is what I want it to do, without thinking about the implementation. It's an iterative process. You say, well, let's see, if I do this, how am I going to implement that? And then if the implementation looks okay, then you say, okay. Otherwise, you may say, no, I have to implement it like this, and so that's going to change what I do, so I can't do that, or I have to change the way I do that, or, and so on. So this isn't just a straight linear process where you sit down and you say, these are the instructions I want, and then this is what the microcode will look like, and then here's what the hardware will look like. You have to be thinking of all three of those at once as you go through the process. I'm presenting it in a linear fashion because I don't think I know how to describe the actual design process and this iterative process. We may get into that later a little bit because I can talk about adding additional instructions. As I mentioned, there are some opcodes available, and so then we can maybe look at what it would take to implement a new instruction and get into it a little bit that way. But that's it for now. That's the instruction set as it's currently designed, and as you saw, it provides a whole lot more functionality than the original and should make it possible to write some actual useful code, though I still don't know what that would be.